Hello and welcome to the last lecture video on NumPy, not the last lecture video on the basic data science modules, but in the subsequent videos we'll be moving on from NumPy to other data science packages. We've been dealing with NumPy arrays, and I've mentioned they are mutable, and we've seen but we haven't seen that in any way yet, actually. So first of all, let me point out that just as you might expect for a mutable array, just as you might expect, we can do things like if we want to mutate this 5 to some other value, that's in position 2, 2, right? Or 1, 1, sorry. 0, 0, 0, 1, 1, 0, 1, 1. And we could simply reassign this value, say to be 10. So before we did the mutation, it was 5. Afterwards, it's 10. Very simple, very similar to the syntax we're used to. It's also possible to change the shape of an array. So an array has a shape, as we have seen already. And I can change this to be whatever I want. Well, not whatever I want, but I can change it as long as that shape is rectangular and has the same number of elements as the original array. So this was a 3 by 3 matrix, so it had 9 elements, and I changed this to a 9 by 1 array. Or I could change it to be a one-dimensional array with no second dimension. Whoops. Typically, we won't do this by manipulating the shape attribute directly. You may remember in my lecture on object-oriented programming, we don't typically manipulate the attributes of an object directly, but instead we typically use a method of the object for manipulating its attributes. When we manipulate the attributes in this way, we are performing a mutation. We are mutating the array. There is a reshape method of arrays which doesn't mutate the object, but returns a new object with the desired shape. So I have a matrix here of shape 20 by 10. The reshape method will return a new matrix with the same values, but reshaped into this 40 by 5 shape. So still this 40 times 5 is 200, 20 times 10 is 200, same number of elements, still rectangular, just a different shape. Notice the original matrix, mat, its shape has gone unchanged. It's this reshape returned a new array with the desired shape. What does it look like when we reshape an array? Well, we've already seen that, but just to give you another example, here's our 20 by 10 array. So here's our 10 columns and 20 rows. If we reshape that, we're going to see these 10 columns condensed down to 5. Why don't we work with a smaller example, actually? So here we have 10, we'll call this mat, 10 rows, 5 columns. And if we reshape this, for instance, to be 5 rows with 10 columns, keep an eye on where this value goes, 0.9679. Oh, whoops. Okay, I read... Sorry. All right, we're going to watch this 0.6149. What happened was I regenerated the array with completely new random numbers. So what we were looking for just totally disappeared. So this 0.6149 ends up here. So essentially the way this got reshaped is that this row just got concatenated on the first row, the fourth row got concatenated on the third row, etc., which is kind of what we would expect. And if we were to go in the other direction, we would instead slice this row into 2 pieces, and it would just get stacked under this one. So if we reshape back to 10 by 5, we get back what we had before. So we cut up rows or concatenate them onto each other. If we try to reshape an array into a shape that has a different number of elements, so we're back to the original here with 200 elements, 20 by 10. If we try to go to 30 by 5, we'll encounter a value error. We can't reshape an array of size 200 elements, into shape 30 by 5, 150 elements, right? What would we do with these extra 50 elements? We don't know. There's a couple of other methods I want to highlight for reshaping arrays. One I already used, but didn't call it out at the time, which is ravel. That unravels an array into a single linear array, one-dimensional array, where we just have a linear sequence of all the elements in the array. So ravel unravels our array into one dimension. Another thing we can do to manipulate the shape is to transpose our array, where hopefully you're familiar with this from linear algebra, but we exchange the columns and rows. Every column becomes a row. So for instance, this column of 0.342, 0.911, 0.592 will become a row. Except instead it will be there we go. Instead it'll be a row of like 0.03, 0.86, 0.62, etc. Since this is the actual matrix we're transposing. And we see the columns and the rows got exchanged. So now instead of having a 20 by 10 matrix, we have a 10 by 20 array. And if we look at this second row here, we have 0.03, 0.86, 0.624. Those are exactly the numbers I was calling out before. 0.03, 0.86, 0.624. So that column got turned into a row. One common use case of NumPy is for doing image analysis, and reshaping images like this comes up fairly often. We might need to exchange, for instance, the dimension in which the color channel resides from being the first dimension to the third dimension, or we might need to concatenate together different color channels to be side by side or something like that. Speaking of concatenating together different arrays, we can combine arrays using a number of convenience functions in NumPy. There's hstack for horizontal stacking, where we stack these onto each other horizontally. So after 1, 2, 3, 4, 5, we have 2, 3, 4, 5, 6. We can vertically stack them with vstack. So these get stacked as rows. Or we can diagonally stack them, which will generally look different depending on the dimensions of your input array. But in this case, it does a sort of combination of horizontal and diagonal stacking. So instead of simply concatenating them together, they sort of got transposed from rows to columns, and those columns got horizontally stacked. So we have two adjacent columns. I'm pretty sure dstack stands for diagonal stack. Depth-wise, depth stack, my mistake. Nonetheless, this idea of kind of transposing the rows into columns and then stacking them horizontally still gives a clear picture of what happened. So that wraps up our discussion of NumPy. There is certainly much, much more to say about NumPy, but as we'll see, we'll be working with NumPy principally through pandas from starting very shortly, by the end of the notebook, basically. And while we'll still use NumPy for certain applications, particularly image analysis or working with scikit-learn, we use NumPy a lot. NumPy will often be lurking behind other data science packages, and we'll use NumPy directly a little less frequently, unless we're taking advantage, for instance, of its mathematical functions or its random submodule. Nonetheless, understanding how NumPy works is going to really help us in working with those, with its children, with its the modules and packages that are built on top of NumPy, because understanding how NumPy works goes a long way in helping to understand how those packages work as well. In the next lecture, we will be discussing some basic plotting and data visualization using matplotlib.